sou muito afortunado de poder estar aqui presencialmente, né? Uma palestra de qualidade internacional. So I was telling them that I'm going to switch to English, my poor English, but let's go. And we are very fortunate to have you here in person, okay? I start my research in robotics in the 90s, so since then I know you. You are a very important person we are transmitting. Professor Goldberg is in UC Berkeley, is one of the most important researchers in robotics in the world. I'm gonna take his biography from Wikipedia, okay? So he defined himself as an American artist, writer, inventor, and researcher in the field of robotics and automation. He is professor and chair of Industrial Engineering and Operation Research Department at Berkeley, UC Berkeley. And he's fellow from IEEE since 2005 for contribution to networked telerobotic and geometric algorithms for automation. He has several awards. He has published more than 170 journal papers, very well referenced. So we are very honored to have you here, and I think that I'm gonna give you the word to start the presentation. Thank you very much. And one more thing. You are here in person, but we are transmitting this talk by our YouTube channel from the Society of Brazilian Society of Automation. So it's go to all Brazil, Amazon from the south to the north, and all the world. So we are very happy, and this talk is going to be a record. So anyone that want to watch later is going to be available. Okay. So thank you very much, Professor Goldberg.
Thank you so much, Fernando, and thank you all to Professor Liu and all of you for your warm hospitality here in Rio. I'm actually having a great time. I love your city. And it's an honor to be here. As Fernando just said, we will record it, so if you fall asleep after lunch, don't feel badly. We can maybe watch it later. All right, so what I want to tell you about is work in robot grasping, and I want to leave time for questions. So do we have until 3 o'clock? Is that still, that's okay? It's not going on? Seems okay. Can we go until 3 o'clock or 3:15? Tell me. That's okay? Real flexible? All right, I don't want to keep you too long, so I'm going to go fast. How many of you know about this Iron Man? Have you seen it? You've seen it? Okay, good. So many of my students I found out are very influenced by this movie, and I love this scene because this is a reality of robots right today, right? They're still very clumsy, they're knocking things over, so it's very accurate. Now, so this is a shot from my lab and our website. These are my real students. They're a fantastic group, and I'm very proud of them. And so what I'm going to be describing today is really mostly thanks to them. So the way I want to do this is in steps. I want to talk about what I call the new wave in robot grasping, and present that as the first wave, the second wave, the new wave, and then, if time permits, I'll talk about some new work that's just coming out of the lab. So let's go back now 2,000 years to the ancient Athens, sorry. And so here we see the great philosophers, the great mathematicians, the great scientists, the great artists of the generation, all gathered together having discussions. And what are they talking about? They're trying to understand the nature of reality. And so at the very center of this image, we see Plato and Aristotle. Now, Plato has his hand up in the air because he believes that to understand reality, we have to start from the perfect forms. We have to start with perfect, ideal, mathematics, we have axioms, and then we can deduce down till we gradually understand what's going on around us. Now his student on the right is Aristotle. Aristotle completely disagrees with his advisor. By the way, it's not the first time that the student has disagreed with his advisor. Now, Aristotle believes the complete opposite. He believes that the way to understand the world is to look around, to look at the stones, the plants, the animals, and then induce understanding and structures and frameworks that will help us understand the world. Okay, so keep that in mind as we start now talking about grasping in particular. So again, it's their hands, and this is Raphael's painting. Their hands are very important. Their hands are indicating their ideas. Now, the idea of hands is really what we're going to talk about. And when we talk about this, I want to talk about the idea of grasping, which is very, very fundamental. So humans are actually very good at this. We can do it from a very early age, and we actually become very good at this. Humans are incredibly dexterous. However, robots, as you probably know, if any of you worked with, those who've worked with robots know that robots are not dexterous at all. That they still, to this day, remain remarkably clumsy. Now, if we could fix this, if we could allow robots to be dexterous, then robots could go around and be able to pick things up and hopefully put them away. So wouldn't it be nice if you leave your kitchen like this in the morning, and then you come back in the afternoon, and everything is nicely straightened up? Right? This is a big goal for many of us. And here's the other scenario, which, how many of you have ever ordered anything from Amazon? I mean the other Amazon, right? Not your Amazon. The other, the new Amazon. Okay, yes, good, you have. And this is actually shot in my own front porch, I'll confess. This is my wife, typical day, ordering a number of packages. And over the pandemic, well, first I'll say that the e-commerce growth in the world has been increasing. Now, this is just the United States, but it's been steadily increasing. And over the pandemic, there was a huge boost on online commerce. And I'm sure this is true in Brazil, too. And what's going on is that just because we couldn't get around, we started ordering, and then that becomes a habit, and we start ordering things more and more. So this has become an ongoing pressing challenge. How do we meet the demand of all of these online orders? And the key issue here is that humans are still very much needed in the distribution centers to be able to pick up these objects that you've ordered and put them into boxes and then sort them and get them out to shipment sites so that they can come to your front porch. And by the way, this all has to be done ideally within 24 hours of the time you press that button. Now, if you go inside these places, it looks like this, right? There's a lot of people working, and they're also in very close proximity. So there's a big challenge of how do you get this done, and especially nowadays when there's concerns about COVID, you want to have spacing between workers. Workers do not like this job, so the turnover is very high. I'm very conscious of the rights of workers, and I want to be respectful. That's very important. And at the same time, though, we do need, these jobs have to get done. So there's a big shortage of workers who are willing to do this work. So there's a grand challenge, and this has been recognized for many years. Rod Brooks here articulated it, that if we could figure this out, if we could find out how to have robots be able to pick up anything, then we'd have an impact in factories, warehouses, and homes. Now, I want to address the issue of hardware for a moment, because the hardware, and I know that we just looked in the lab, it was just beautiful designs, and I know there's many designs out there for complex hands, maybe anthropomorphic hands that look like human hands, and then there's soft fingers, all kinds of different designs. But I want to make a plug here for the very basic parallel jaw gripper. So this is the most common industrial gripper. And it just has 2 jaws, 1 degree of freedom. So it makes contact at 2 points on an object, and it's still very popular, but keep in mind, this is very simple hardware. Now, I want to claim that actually simple hardware, you can do a lot with that hardware. You don't If we can solve that, in some way we need to solve that before we go into more complex hands. That's what I believe. So this is my proof, existence proof, that you can do very complex things with very simple hardware. Now this is a this is a surgical robot. Excuse me. With two parallel jaw grippers doing origami. And the thing to note is this is teleoperated, right? This is not autonomous by any means. But it's able to do incredibly complex motions. Sorry, I have a little bit of a cough. I do not have COVID, but I had COVID. So I'm going to take this little bit of medicine. It should clear it up. Okay. Yeah. Real time. All right, so now, hopefully everybody agrees that you could do a lot with these simple hands, right? Now, I even want to say, even going even further, look at chopsticks. Okay, you can pick up very complex things, even things that are covered in viscous, very low friction objects, and you can pick them up reliably. So you don't need very fancy hardware. All right, the other thing I want to mention is advances in sensing. So most of you are familiar with LiDAR, depth sensors. That has been a huge advance. In fact, everybody talks about deep learning and depth in the learning systems in these networks. But I think it's also interesting that around the same time there was a revolution in deep learning, there was also a revolution in depth sensing. So the Kinect camera, if you remember, came out around the same time, 2012, and provided a really nice low-cost way to collect depth data. And the challenge, of course, is that this depth data is not particularly high quality. So here's an image on the left. Oops, sorry. It's been played. But this, you can see here that the point cloud image, this is a depth image, but it's actually got gaps and holes in it. So whereas it does give us a good estimate, finding out the exact pose of a three-dimensional object in space is still an open problem. It's a very hard problem, and it's especially hard when that object may have specularities or transparent surfaces. Then the depth camera completely falls down. The other thing I want to point out here is the issue about friction. So here we command our robot to just push this object across the table. Come on. There we go. And we do the exact same setup multiple times, and with the same motion, but notice that the object ends up in very different poses. Why? Well, this is not surprising, frankly. If you push things, this is what happens. Well, it just turns out there's very small variations in the microsurface, and that in turn affects the friction. So it doesn't take much. Just even a grain of sand can cause the object to pivot on that grain and wind up in a very different orientation. So this is a very deep problem because people talk about, well, where are the hard problems out there? I want to say this is an undecidable problem because even if I have better sensors, I still can't predict exactly where that object's going to go. I mean, because that surface topography is very, very subtle, and I can't sense it because it's underneath the object. And it may change. Every time I move, that surface is changing because of shear forces. So right here you have an undecidable problem, right? We don't know. No one, I don't think this will be solved ever. I'll be able to predict exactly where that object's going to be. Now you might say, well, who cares? Well, it turns out that if you want to do grasping, you do care about this, right? This is a big issue because you really need to know where things are, but we're going to be able to pick them up. So here's another way of thinking about it. If you're a robot, so put yourself in the position of being a robot, and I tell you to go and clean up after a dinner party. So this is what your world looks like. Your sensors are noisy and imprecise. Your actuators are actually have noise and imprecision in them. And there's noise and imprecision in the fundamental physics of friction. So it's not surprising that robots are still very clumsy. So I want to just really emphasize the same point, that it's the uncertainty in the physics itself, uncertainty in the perception, and uncertainty in the control that all combine here at the uncertainty at the end effector. And that makes it extremely difficult to be able to reliably grasp and hold objects. All right, so that's a setting. Now, I'll tell you what I see as the first wave. So this comes back to Plato. And this is really the wave of the way robot grasping was done for a long time, 50 plus years. Some of us remember those days, and still, in fact, it's still the majority of work in robot grasping has this flavor. It's basically based on the beautiful mathematics and theory of wrench theory and mechanics. And this has been developed over hundreds of years, and many top researchers in grasping basically applied this theory to the problem. And I had the chance to work with Shankar Sastry, Rujana Baichi. A few years ago, we used Shankar's book, Robot Manipulation. It's a very elegant book, and it's all filled with images like this, analysis, and if some of you may be familiar, the idea is that you want to understand the precise, if you know the positions and orientations of points and contacts in space, then you're trying to determine if the object will be in equilibrium. And so you have a physics problem, so you can set that whole thing up, but the problem is subtle because of the uncertainty. Now, in the Handbook of Robotics, which is it's now 1,000 pages plus, there's a chapter on grasping. And if you go into the chapter, you could go all the way up until the end of the chapter. It's about 40 pages. And at the very end, there's this sentence. When a robot identifies an object to grasp, its knowledge of the object's pose and geometry are not perfect. So I consider this one of the greatest understatements of all time. I mean, this is an amazingly important point, and it's only mentioned sort of in passing at the very end of the chapter. And this is, unfortunately, this is really the state of the art. This is the first wave. Everybody has looked at grasping as a physics problem, where we know all these forces and torques, and now we want to add them up and see if the object is in equilibrium. Well, we can formalize that as we have a state of the world, x, and we have a control, u, that's the position of all the fingers and joints, and we want to determine a policy that takes as input x and returns a control, u, that will, in this case, make sure that the object is in equilibrium and is being firmly held and can resist external forces. Okay, so that's just a very simple way of putting that model. Now, this again, assuming that everything is perfectly known. And it isn't, unfortunately. We don't know x exactly. We don't even get to know u, right? We can make a command, but we don't get to actually control exactly where those points end up. So this is the starting point for what we started calling the Dexterity Network. And this is joint work, and I want to give full credit, majority of credit to my student, Jeff Mahler. Here, this was his PhD work. So we started by thinking, okay, all these things are not known, so let's treat them as random variables. And we'll make a graphical model indicating their relationships. So, right, this is saying that the contacts here are a function of the pose of the object in space, the pose of the gripper, and the object's shape, right? All of those are, these are variables, but they're going to affect this variable. So it's conditional on the state of these variables. The contacts are going to affect the normals, and the normals and the friction are going to affect the forces that are applied. Similarly for the torques, and then ultimately this thing is going to determine the probability that the object is successful. Okay, whether it's a variable here, Q, and it's either successful or not. Now, one way we can tackle this is to try Monte Carlo integration. So we have this very uncertain variable, but it has all these constituent parts. So what we're going to do is sample. So here's an illustration. So we have a red object here, and a typical object in the CAD model of a typical object usually is something like 1,000 facets. And a grasp is some pair of facets. So that means there's about 1 million different ways to grasp an object. Okay, so now these are 4 of those million. And for each of those, I want to now check what's the probability of success for that particular grasp. So I'm going to do this Monte Carlo integration by perturbing those random variables and sampling essentially from all those distributions. So if the object is, the translation is slightly off, the rotation is slightly off, the friction, the center of mass, all those variables, right? I'm going to perturb those, but then check for each one of those combinations if the grasp is successful or not. So this is indicating green is it's a successful grasp. Again, I'm applying the first wave elegant theory, but perturbing it now because I don't know the exact values. And the red indicates that it's a failure, and then I sum that all up, and I get an estimate. So right here is an estimate of 22. So that's saying that there's a 20% chance that this grasp will succeed in probability. Okay, so if you look at it, it makes sense, does it? This one on the right is much better, more robust, because this says 90%. So in 92% of the samples, this worked because it's sort of self-aligning. So even though there's small errors, they sort of self-corrected. So this is what we're looking for. These are robust grasps. Okay, now we have another problem, which is perception. Perception is not known either. So we get a variable y, an observation, but what we really care about is x, the state that gave rise to that observation. So we don't know exactly what we're going to get. So what we do here is we say we're going to take a LiDAR image, a 3D image, remember it's noisy, of the object. Then we're going to do a state estimation. And there's a variety of good methods out there for trying to understand the state from the image. So we'll apply something like that, least squares or something to fit the data to the model and come up with an estimate for x. And now we'll run that estimate with our policy and come up with the best grasp. So that's what that is. Now I'll show you how that works. So here's an example of an experiment in the lab. Okay. Now we computed a beautiful grasp, very robust for that object, but our state estimation was wrong. So that would have worked beautifully if the object was in a different orientation. But it's not. And so we went and grasped it with every good intention, high probability of success, but our state was wrong. So we fail utterly. Okay? So we need to also have an uncertainty model in our perception. So now we want to essentially treat that as another random variable, right? And now I want to estimate for a combination of the sensor values and estimate what is the probability of success now given y. So I want a policy that takes as input the sensor value and then finds a control that will work best for that sensor. So this leads us to the second wave, because now I'm essentially trying to apply a model to infer the state of the system that I don't know. And this is really now we're in the realm of Aristotle. Remember, Aristotle was all about collect data, right? He wanted to look at the birds and the rocks and the plants. So he was all about collecting data. So actually, that's the realm of deep learning. And deep learning has a long history, but as everyone knows, has this huge burst of activity in the last decade. And so deep learning has been applied to problems in grasping. And a number of researchers immediately tried this out. And so in the two of them, this one in particular was work at Carnegie Mellon. What they did was they took a fair number of images of objects, and they hand labeled them. So they put in a little bounding box to indicate that's where the grasp should go to pick that object up. Okay. Now this group over here was at Google. And they said, well, we don't want to do that. We don't, that's not enough data. We want a lot more data. So what we're going to do is actually have robots doing self-supervised learning. So they're just put these objects in a bin, in these bins, have the robots essentially look down and just try grasps repeatedly in a reinforcement learning kind of setting. Now, this was very interesting. 14 robots working 24 hours a day in the lab. And so this is the dropping in error, right? So over time, they got better and better. Now, one important thing to just note, if you look carefully here, is that this is the asymptote. So they're getting down here slowly toward about 20%. That means 20% of the time it fails. And what's also important is this is a log, it's a log plot. So this was at 10 million grasps. So that's about a year's worth of data of this thing running 24 hours a day, 14 robots. So you're getting down to about 20% error. So what you really want, for industry, we want to have errors closer to 5%. So if you follow that log, well, that looks like it's going to take maybe another 10 years or maybe 100 years to get there, okay? So there's a problem. So these kind of physical experiments, they sounded good, but they really, the amount of data you need is exorbitant. So they did not succeed. They're still trying, by the way. But what's happening meanwhile in computer vision? Well, computer vision has had enormous success. And this, I always love this example from YOLO. This is the James Bond movie where it's running in real time. In fact, this is superhuman labeling. So it's identifying objects in the scene and labeling them. And if you look closely, you can see there's a fair amount of false positives and false negatives here. But it's actually pretty cool. It's working pretty well. And this has been the huge success, by the way, in Google and Facebook, and now we're using these tools all the time and running them over your images, by the way, whenever you upload something. So it's used to label things and search for objects in space. So what happened there was, well, they had a very large data set, and that was ImageNet here, which was extremely valuable. This was millions, tens of millions of images hand-labeled, and they used mechanical Turk or various tools. Basically humans looking at the images, drawing the bounding boxes, and labeling what they were. So they just accumulated this as a work over years and years of manual labor to collect this data. So it was a huge success. So it seemed like there's a critical mass. If you got enough examples, the system this network could start to generalize. That was a breakthrough in 2012 by Jeff Hinton and a number of others. So what we started thinking was, could we do something analogous in robotics and apply something similar to our problem in grasping? And again, we're talking now about supervised learning here, not reinforcement learning. We're just talking about supervised learning. I'm going to give it a lot of examples, and then I want it to learn to recreate or generalize to new examples. So what we need is a lot of examples. So this is a plot of the number of 3D models out on the internet. And so it's growing. It's grown quite a bit, and it's due largely to 3D printing and gaming. So people are putting their 3D models out on the net. And so our question was, again, could we come up with a data set that was analogous to this one in computer vision, ImageNet? We call it, again, Dexnet. And here we want images of, we have 3D objects. We want images of those objects with the grasps and the quality, the reliability of those grasps, probability of success. So that's what we started out to do. We wanted to build a large data set and using CAD models. So we went out on the internet, we found a lot of these models, but they were often, like this, weapons and aircraft. That's because they're gamers, right? That's what they are modeling. But those are not things that we commonly want to pick up around the home. So then we went out and we started collecting these kind of objects just by a lot of manual labor on our side, just downloading things we saw, cleaning up the models, making them watertight, scaling them, putting them into consistent formats. And then we also augmented those with some, this is shrink wrap, right, where you put something around a piece of cardboard. So that was very typical for the kind of things we expect to see in warehouses. So we just basically spent about a year collecting data, objects. And we particularly were on the lookout for things like this, which we called adversarial objects. These are objects that are really challenging for a robot gripper because they have a lot of small, strange surfaces. So we wanted to really push our algorithm. And we also put these into a network of relationships, and I'll just touch on why for a second. But the computation here is non-trivial. So if we have 1,000 objects, 1,000 facets, we have 1,000,000 grasps. In each grasp, we're going to look at about 1,000 perturbations. So that's 1 billion grasp evaluations per object. And then we have, let's say, 10,000 objects. So we're getting pretty big numbers of computations there, large data. So we spread that out. We do it over over, in this case, AWS and Google's cloud. We also used a trick from multi-arm bandits to be able to speed this up. And so the idea here was that we wanted to use a prior to find good grasps. And the key was that if we have similar objects, so we found a grasp on this, and now we have a new object, we could index a similar object. We could basically use that as a prior to find good grasps on this one. Similarly, if we're analogously, this is the same object, but we have a grasp that's slightly different. So we want to use that as a prior. So we needed a similarity measure. So again, we went out to deep learning. Deep learning was very nice around this time. This was in the late, it was like 2018, 2017. This new technique had come out called Object Similarity Network. And the multi-view deep convolutional neural net. And basically you could train that with simulated images from different perspectives, and you could then say all those are the same image, right? The images are all of the same object, and then train a network, and it was remarkably able to now take a new object and find index into similar objects in a data set. So we did this, and we basically incorporate this similarity measure into the kernel here, where we're basically trying to determine the similarity between two objects. We can use the network for that after it's trained. And then we use that is to weight modifications to a beta distribution, where if we get a successful grasp, we're going to weight it by we have a prior grasp or prior object. We have a grasp. If it was successful, we add to the alpha. If it was unsuccessful, we add to the beta variables. And that allows us to basically converge on an estimate of the probability of success faster than if we were just starting from scratch. Okay, so this shows you basically, this is evidence of this, that if we have a large enough data set, so you don't see much improvement here, but here, when we have a very large data set, we have an object, we have a lot of similar objects, so here we get a very fast convergence to highly reliable grasps. Okay, so that was a little detour just in the computational aspect of how do we solve this problem of doing all this compute for a very large set of objects. So this brings us to the new wave, and I'll make a quick mention here of a book that we wrote with some science educators called How to Train Your Robot, and it's basically the story of what I'm telling you, but for 8-year-old kids. It's available online, so if you have any 8-year-old kids in your life, 8 to 10, and you want to get them interested in STEM in particular, you can check out this book. But there's a part in the book where the kids are all trying to pick up objects clean up their classroom, and they're having trouble, so they go to the local university, and basically the university explains, the students in the lab explain, well, here's how you do it. You basically do this in simulation, and you try out all these objects in simulation, and one of the girls says, oh, you mean the robot is dreaming about how to pick up the objects? And then the professor says, exactly. So that's basically right, because that's what we're doing. The robot is dreaming or simulating the world and learning how to pick things up. All right, so I want to make a quick statement here about sim to real. Sim to real is a really, I now think it's the most central question in robot grasping, at least. And many of you are familiar with this story with OpenAI. They had a robot that learned how to manipulate a Rubik's Cube. It was just very simple, just basically being able to turn one side of a Rubik's Cube. It was pretty straightforward, but it took like 150 years of compute and experiment they had to use to get this to even perform at a very simple level. This is called crossing the reality gap. And this is that when you simulate things, as I'm advocating here, then when you move into reality, things often don't work. So what's often done is what's sometimes known as domain randomization. So what you do is you just basically throw uniform noise over the problem, and you hope that the robot will learn, or the deep learning algorithm will learn a policy that's robust to this noise. And it just shows you, like this is a typical setup where they're throwing random noise into the backgrounds. And I don't know about you, but this bothers me because it feels like that's so random, right? It just like, it doesn't feel like there's any principle. You're just sort of randomly generating patterns and putting them behind, and you're trying to make the robot ignore the image, all this image except the 3D structure. So I could say more about this afterward. But that's very different than what we were talking about here, which is what I call structured domain perturbation. So you're not randomizing the inputs, you're actually perturbing them, but around a distribution that you hope is somewhat representative of the real distribution you'll encounter in reality. So I think that is going to that you can yield better results. We did the same thing with images, by the way. We characterized the sensor. So we have a fairly high resolution depth sensor, but we characterize the noise in the sensor as well. So the result of this is we get this large set of data. This images from the sonar, the LiDAR, the grasp, and then the probability of success for that image. And now, once we do this, we can do this offline. Essentially, we generate this data set, and this is about 6 million examples of both positive results and negative results. So where it succeeded, where we have a high success rate, and where we believe it will not succeed. And then we train a network on that data set. So this is a standard thing. We just want to find a value here, theta, which is a vector of all the weights. They'll minimize the loss. And the loss is the difference between what we know to be the value that we've computed and what the network puts out. So when we do that, and that's very established classic supervised learning, then we have that optimal value of theta. Now we can use this. If we give it as input a sensor value, and it should come out with an estimate of what's the probability of success. So we did this, trained this network, and it converged fairly quickly. And then we're going to run this, so we now give it just an image, run it through the network, and as we run an optimization around that to basically find a grasp that will have a high probability of success, and then we execute that. So this is what we called Dexnet 2.0, and it worked surprisingly well. This surprised me because I didn't think this was going to be able to incorporate this error in the sensing, because that is a very fundamental issue. We had these good model of error in the grasp, but we didn't have a model of the error in the sensor. But this worked surprisingly well. So well, in fact, that Jeff then said, I'm going to try to push this even further by actually simulating objects in a heap. So again, he would simulate objects from our data set, our Dexnet data set, dropped at random into a heap, and then we knew, once we dropped, we knew in 3D, again, this is in simulation, we know where all the objects are in space, we know where these grasp points would be successful or not, and then we could train the system to take an image of a heap. So here's the example of what this is. This is just a RGB image of the heap. This is what you get out of the depth camera, right? And it comes out overlaid with all these potential grasps. Here's one iteration where this basically cross-entropy method reduces the number of grasps, and it's basically trying to find an optimal grasp. And this is the grasp that it computed using that network, grasp quality network, to say this is the one I believe is going to have the highest probability of success. And then we execute that. So here's the system running with completely novel objects. So these are objects it's never been trained on. In fact, if you look closely, you'll see that these objects don't even obey we were assuming all the objects were rigid, right? There's a number of objects in here that are deformable and a piece of cloth, quite different than what's been trained on, but it's still able to successfully grasp these. And this was very surprising to me. I mean, I've been working on this problem for 35 years. I like to say we made very little progress. But this was a day when I walked in and I was like, this is progress. And the system was reliably able to clear bins like this. So we would just dump things in. And we were going out to local garage sales and grabbing stuff. We had boxes and bins of all kinds of random stuff, and we just throw all kinds of things in and this thing would work, picking them up reliably. Now, we got some news, we got some nice coverage from the press about this, and we got some interest from companies who wanted to put this into practice. So the first thing we learned, though, was that they had a different model of grasping. Remember I was telling you about the 2-point gripper that I was a big fan of? Well, they said, no, we use a 1-point gripper, a suction cup. That's what industry uses the most. And so we thought about that for a little while. We thought, wait, maybe we can apply the same framework to suction grasping. But now we need a measure of quality, going back to that first wave. So we said, well, look up what's the measure of quality for suction cups. And we went into the literature, and we couldn't find one. Now, I still believe there's some things out there, but there really wasn't a nice, clean model of grasp quality. So we developed our own, basically, which is based on how the surface of the suction cup conforms to the surface of the local object. And we also had to look at the grasp mechanics to develop a wrench analysis, because these suction cups are very poorly resistant to twist about their main axis. So we had to build this model, and then we ran everything through the same way. So we now say, here's a candidate grasp. Here, we take all these perturbations, we sum them up, and we come up with a color that's consistent with whether the grasp is likely to succeed or not. So this is an object that's sort of labeled with all these grasps, and these ones are highly likely to succeed, and the red ones are not. They have low probability of success. So now we can do this. So we see a bunch of objects in a bin. We run this analysis, and so we can label them, and we want to find these high probability suction points. So now we can do this. So we had a suction gripper, and it's able to pick things up like that. Now, we had these two different modalities, suction and grasping, so we thought we'll put them together. We call this ambidextrous policy that has two different arms and end effectors. But we want to decide which one we should use. So the key there was just putting these into a common metric, a metric that we can compare the two. And basically, so now we're trying to maximize, well, which one is a higher probability of success? And then choose that actuation, either gripper or suction. So here's what it looks like. So we have these two tools working side by side, and the system is scanning the scene and then computing the highest grip point for each, and then whichever one has the highest probability, it goes and executes that. So essentially balancing the load. And you can see here the failure, because the system assumes objects are rigid, so it doesn't know anything about porous objects, so it fails. One thing we had to do was introduce a little bit of memory between grasps, because if we didn't do that, it would keep doing this over and over again. So it has to know when it failed with one modality, try it with the other one. Okay, so this is the basis of our paper that was on the cover of Science Robotics, that basically, this ambidextrous, two forms of grasping, right? This thing cannot be picked up with a suction, and this thing cannot be picked up easily with a gripper because it was too wide. So I also want to note that there's still a lot of objects we could not pick up. And I think it's really important to, show your failure modes. So this thing is it's impossible to suction. It was too wide for the gripper. These are transparent objects. We couldn't see them well enough with the camera. This was too heavy. Just the suction and gripper failed on it. And these are very interesting, right? These we could not pick up, because suction and parallel jaw gripper just doesn't work on either of those. If you have a magnet, you could pick them up, but otherwise, you're out of luck, okay? So we got a chance to display this thing to someone you may recognize from the other Amazon. That's Jeff Bezos. And we're demonstrating this. And okay, so what happens here is his assistant just threw his shoe into the bin. If you look closely, it picked up the shoe and threw it in there. We were amazed that worked, because we just hadn't had any experience picking up shoes. So it was very lucky. And Jeff Bezos told us at the booth here that we were solving a problem that's very important. The next morning, my students called and said, we want to start a company. So that's what started Ambi Robotics. So Ambi Robotics is now a company in Berkeley. It's still somewhat new, but we're up to 40 people. And this is a little video from the company. This is showing the setup, the system that we have built, and it's basically sorting packages. So it has to be able to pick up anything that you would send in the mail. So it's all different kinds of weird shaped packages, and then it sorts them, it scans them and sorts them by zip code. But it turns out this is a very, very big problem. And so all over the world, this is being done. So we're selling these systems, and we just got an order for 60 of these systems. So we're building them as we speak. So if you're interested, we're still hiring. We're hiring. So we're happy to talk to you about that. Okay, now that's what I wanted to, the main things I wanted to tell you, first wave, second wave, and the new wave. And let's come back now to this image of the philosophers and the scientists and the artists all talking. And if you look closely, they're all, Raphael painted this to show their hands were actually in all kinds of different poses. So it wasn't just Plato and Aristotle. There are all kinds of different ways of apprehending reality. So that's what I want to leave you with, which is that we haven't solved this problem. But by putting a mix of Plato and Aristotle together, we're able to get something that's making a certain level of progress. But I think to get this problem really solved, we're going to need other methods, new methods. And that's where you guys, the students out here, are going to really be able to make that advance for the future. Now, I also want to say I'm not too worried about robots taking over from humans yet, because as you can see from this video, humans are pretty amazing at manipulation still. So don't worry, anyone who's fearing that robots are going to take over all the jobs, that's not going to happen. Okay, good. So let me stop there. I want to thank you guys, and then if there's time, I can tell you about a few other projects. So thank you.
Okay, thank you very much. Wonderful talk. Okay, we can open for questions. I have to check here the chat in the YouTube.
Oh, people online?
Yes,
Okay. And while you're thinking of some questions, I can just tell you about some other things real quickly, which is new projects. So I heard a few minutes ago that many of you are using ROS. So I'm really happy to hear that, because we have been very excited about ROS, in particular ROS 2. Now, we built a cloud robotics infrastructure for ROS and ROS 2. So it works for both, but we're really trying to look for beta testers to use this in ROS 2. And what it does, you can find it online under Fog ROS 2. Fog is like cloud, but with ROS 2, and this has actually been released by ROS 2 in the latest release about a month ago. And it allows you to do experiments with grasping, SLAM, and motion planning, where the computation is being done in the cloud. And the idea is that in the future, you'll be able to move your nodes that are local into the cloud very painlessly, and then they'll operate there. So it makes all the connections, it encodes the data, encrypts the data, and everything without you having to worry about it. And interestingly, and this surprised me, that we are able to achieve speed ups over local processing, right? The local processors on a robot especially are very slow, but the cloud has so much access to GPUs and multiple CPUs that you can get dramatic speed ups. So speed ups on the order of 30 times. 30 times if you go to the cloud. So I invite you to try this. You can just go to FogROS 2 and just search in Google. It should come up. But then there's a GitHub repository, and you can download and play with it. Or you can go onto the ROS 2 repository and pull it up there. Okay, so that's one thing I want to tell you about. Any questions? I have more. Otherwise, I'll tell you more things. All right. This got moved in the order. Okay, I'm going to just show you. Here's, we've been looking at the problem of optimal transport of objects, again, for the warehouse. So in a warehouse, you often want to move things very fast from point to point. And so Jeff Ignowski, who's a postdoc in the group, came up with this algorithm using optimization, iterative optimization, to compute these motions that are very, very high speed and yet obey certain jerk limits that are inherent to the robot. And so you could also, what he realized is that you can also, it could also be used to control limits on the on other forces, inertial forces in the object, and all right. But now I'll just show you that we were talking about it, and the idea was we basically got it so that you could take a glass of wine, and the robot could move it over to the other side of an obstacle without spilling a drop. So then I was telling someone about this, and they said, "Oh, well, you know, this is an old trick." And I said, "What do you mean?" And he said, "Well," and then basically he taught it to me. So here's the trick. If you can see, I'm holding a glass of wine in my hand, okay, and you look closely. So it doesn't spill. So you can win money at bars with this, all right? Just so you know. All right, that was a little aside. But there's a paper on this, the mathematics and the optimization that's required to be able to do this. Humans, by the way, again, have very high torque, relative torque capabilities, much higher than most robots. We can't get our UR5 to go that fast. All right. Questions? All right, I'm going to go on. Then this is another recent project, and here the challenge is to we want to take that little weight on the end of a rope or cable and manipulate it with the robot to a desired point on a surface. Okay, fairly simple idea, and this is an example of what we're trying to achieve. Okay. The reason I bring this up is that we want to talk about this in the context of real to sim to real, which is our new way of thinking about the sim to real problem. So this problem is interesting because it actually is something you do encounter, and you know, if you're fishing or let's say trying to make a bed or a shuffleboard, right? There's all kinds of things where you actually launch something and you want it to reach a desired state. Now, if it's a ball, then it's often ballistic, right? So now you're just dealing with ballistic trajectories. So it's not quite as hard, although if you want to take into account wind and temperature and all those other factors, it does become much trickier. But if you're dealing with a surface, it's there you could run into friction, and now it's much harder. And in this case, you have the deformability, the very high dimensionality of the rope or cable. So it's very hard to predict what the cable is going to do with that object. So sim to real is where you train something in sim and then you deploy it in real. And there's another variation of this, but what we want to argue for is real to sim to real. And what that is that we have to spend time actually tuning the simulator. So you want to collect a certain amount of real data and then use that to train the simulation, so you get a very accurate simulation of the real system. And this comes back to what we were talking about the structured domain perturbation, because then you can do that, and then you can deploy it back into real, and hopefully you'll have some chance of working. So here's what we did was we basically looked at simulators for this problem, and this is called Isaac Jim from NVIDIA. What we had done was we collected lots and lots of real trajectories with our robot, and this could, by the way, be done unsupervised. Right? You can reset the weight and then rerun this many, many times overnight, collecting lots of data with an overhead camera, and then we try and fit the simulator to produce similar trajectories. So these are two different simulators. This is something called IPC, which we had a lot of hopes for, but it didn't work really as well. And the key thing we did, though, is we tuned the simulator. So here's the real data, and here's the simulated data. So we spent a lot of time worrying about how to tune that simulator so it would reflect the real system. So then what we do is we take the real data, we tune the simulation, and then, let me go back, then we use the simulation to learn a policy where we inject noise into the simulation, but at least we have a pretty good idea of what the simulator, what reality is going to do, and then we train a policy, and then we evaluate that. So here's the result. This is with using a Gaussian process methods. Basically, this is what you want to pay attention to here. The median error, which is 100% is the full length of the cable, and 0% if you get it right on the, you land on the target. So here we're not doing very well, right? But if we use this method here, if we just take all the real data, and we don't have very much real data, but you can say a few hundred data points, we could get about 15%. If we just use the simulation data, then we get down to 14%. But if we use combination of the real to sim to real, and this also involves training with both the real and the sim, we get it down to about 8%. 8% errors. Now, and it's different for different objects, different cables. Again, we have to rerun the whole loop when we change the cable, but there's an example of a success. We just threw a quarter on the table, and then it was able to pull the weight over there. Here, in full fairness, is a failure. There's a failure. Okay, so it was way off. Okay, so that's like probably like 80% error. Now we can characterize this. So once we train these, we can then start to look at where the errors accounting resulting. Like here, this is a very large error, but this is where your target is off in the corner, and it's sort of outside. This is the reachable workspace, and this is the non-reachable workspace. It's beyond the reachable workspace. But a lot of our targets are out beyond the reachable workspace, so we're using that, relying on that motion to get there in all cases. So this is showing for this cable 2, and this is cable 3. So you're seeing they're fairly similar. The star is the target, and then you're seeing a distribution in an ellipsoid of what the actual results are, how far it is able to reach after training. So I'm very interested in this question of sim to real, and there's a lot of simulators that are coming out there, and this is a broader question, but Isaac Sim is actually very really advanced, and they really put a lot of resources behind it, and it's very effective. But I want to say that we're still in this case where tuning these simulators is extremely difficult, and I get a lot of pushback from my colleagues in robotics, and I wanted to show you this as an example of why the simulation is actually tricky. And I think the mechanical engineers here will appreciate that if you put this is a double pendulum here, that when you run this, so we want to simulate this thing, and it's pretty straightforward. There's no friction really, but as you let this run, it will soon start doing some pretty. All right, there, he didn't let it move. So now he's going to unclip that clamp, and now you have a real double pendulum, and you guys know what happens, right? It starts doing this, right? So your simulator is you're going to be able to model that? I don't think so. So here's, this basically shows you, one simulation run of the double pendulum, and it quickly becomes, very chaotic. So the idea is that if you wanted to predict, if you wanted to have a controller for this, you would have, and you wanted to do your sim to real, you have almost no chance of being able to simulate this in some deterministic way. It's just going to be highly sensitive to initial conditions, right? So you just goes completely, none of these points are near to each other. Okay. So that's where I want to leave off. I have more to say, but I'm going to stop now, and I'll be happy to take any last questions you guys have. Obrigado.
I have one,
yes.
but I think that you are presenting several interesting things. I don't know if I have to interrupt you because very interesting.
No,
but two things, two questions. One is, I think that it was in the plenary of Matthew Mason in 2019 in case, and he says something about the clips that is very hard to grasp. That, and I cannot recall, but he was saying that he solved the problem to grab the clip. Is it solved, this problem, or?
This is Matt Mason talking about an ellipse, did you say? Or what object?
A clip.
Oh, a paperclip.
Paper clip. Is it still an open problem?
Yeah, as far as I know. I'd be curious if Matt's very good at grasping, so if anybody can solve it, it would be him. Okay. But no, a paperclip is just so hard for the practical reason that the parallel jaw gripper generally can't get low enough, right? It's too small. I believe you could make modifications to a gripper. For example, it has a slightly deformable inward jaws that you could be able to pick up those tiny things. So I think it could be solved. Maybe Matt has done that.
It was a combination with a suction cap, or something like that, I think.
Suction is going to be tricky. Yeah. So suction is a good example where, like a washer or a paperclip, it's very hard to get a good suction grip on that. Okay. I do think, one thing I've been interested in is this question of can we design worst case scenarios, adversarial cases? So this is another one. This is an object that we designed in the lab that was specifically designed to be difficult to grasp. So I'll pass it around if you want. And what it is it started as a cuboid, or an octocubahedron. But basically, we started perturbing all the vertices to make sure that there's no parallel edges to this, and that all the surfaces have little dimples on them, pyramidal dimples, so that the suction you can't get a good suction grasp on it. So if you want to pass that around, this thing, so we 3D printed it, and we're trying to find examples. So I encourage you also in, I think this is helpful for robotics, is for us to find examples where things don't work. Computer vision, many of you are familiar with the adversarial images. You can come up with a process to optimally perturb an image so it will be misclassified. And I think we need to be thinking about similar things for grasping. How do we take an object and make it hard to grasp? Again, because I want to always be looking at this boundary and trying to push this problem further. Believe me, because if you're in industry and you're actually trying to do this for real packages, you will encounter these failure modes. And I really think that we're going to be able to make progress, just like we did in computer vision. Never get a system that's going to work 100% of the time, but we can start increasing that probability of success. And that's really a really rich problem, and I think that's going to be something of a problem for the next 20 or 30 years for roboticists. So there's a lot of work to be done. And I want to say for all of you who are just starting out and thinking about what your dissertation topics, this field is filled with unopened questions, unsolved problems. So we're lucky in some way. Our field is hard, but there's a lot of opportunity for research.
Yes. I have two questions. Maybe, if you don't mind, going back to what was the breaking point between the second wave and the new wave? This is one question. And second, why you have to use rigid fingers instead of soft fingers, so.
Excellent. Okay, thank you, Lou. That's a great point. Both are excellent. So the difference between the second wave and the new wave was essentially the idea of calibrating the sensor with real data. So one of the things is that we tried least squares, all kinds of other methods where we would have to try to basically take this data and fit it to a plane and then fit it onto the object. The problem was that we really weren't trying to find planes even. We just wanted to say we have this data of there's like these points in space, right? That was what the 3D sensor was giving us. And we wanted to find, you have a surface of points of space, and you want to find basically a place to put your gripper that has a high probability of success. So it couldn't even be, that problem can't even be framed in a classical way. So that was where we went really to this full Aristotelian model and said, okay, we're not going to even try and solve a piece of it. We're going to put the whole thing into this model, but we're going to generate all the examples in a very systematic way. So it embeds the first wave because when we do all those tests, we do use the classical mechanics to check. But then when we integrate them all up, that was the first wave of adding in the stochastic error into the grasping model. But then we add the sampled error of the real sensor. And that was the new wave when we put that layer onto it. To your second question about soft gripper contacts, you're exactly right. Thank you for asking that. So one thing I glossed over here is that a lot of the contact models are point contact, the classical models from the first wave, and you just assume that you can apply cones of friction, especially in particular for antipodal pairs of faces. There's also something called a soft finger contact, and that can resist wrenches around the grasp axis, right? That's the approximation that we usually use in the first wave. But when you really grasp objects with grippers, there's much more going on there. And it's actually true with human grippers in particular, that when you grab something, I could grab it on two edges, because what happens is my fingers conform to those edges and give me actually very nice holds on contact. So that's actually where we've been looking lately. And thank you for bringing that up. So in practice, the parallel jaws in many robot grippers will have these soft deformable pads on them. And so here's an example. If you pick up a cube, you can pick it up at two corners pretty easily if you have such pads. Under the classical models, you'll never succeed holding an object by corners. They generally it's not even well defined what's the surface normal at a corner or edge. But people do that all the time. So we are working to model these deformations. And so we have a paper that was in the ICRA, the Robotics and Automation Conference last month in Philadelphia, where we're applying a technique that basically we've been trying to use simulation to model those deformations. And the simulation actually gives us better performance in real experiments. It matches more closely, but it takes hours to compute. So the new idea is that there's a method from computer graphics that can speed that up, and it's called incremental potential contacts. And so we're in the process of adopting that and trying to make that run so that we can run these 6 million experiments. Basically, we calculate that would take like 2 years of compute, and we don't have that much compute power. But we're trying to speed that up. So we are trying to model that, and I think that's exactly the right frontier to being able to get this next step up, because that's what the real robot has, those pads, and it makes use of that in a way that we're not modeling yet. So thank you for asking that. Yes?
Thank you.
One follow-up on his question. What if you put gloves on the gripper?
If you put gloves, so then you have more soft?
Right. Mm-hmm. Does the success probability increase?
Well, yes and no. Here's the challenge is, so a lot of people have been proposing this idea of these soft grippers, and they look basically like, they're like pneumatic, inflatable, just sort of envelops the object. And that actually does work remarkably well, picking up a lot of objects. The two challenges. One is it's not that practical for industry, because you often get this problem where it picks up two objects instead of one. So you get this double picks. And industry really doesn't like these, because you end up putting packages in the wrong zip code. They don't like that. Or you put two products in the customer's box, and again, industry doesn't want that. So that's one. The other is, a lot of times, if you want to do what we're doing, which is scanning the object, once you envelop it like that, then you lift it up. Now you can't see the object very well to figure out where the zip code is. So that's why suction is particularly helpful, because you just have, essentially the object is still very exposed, and you can do an inspection on it.
And the other question was, in a real cluttered scene, how long does it take to compute the grasping model?
Great question. So in a real cluttered scene, like these bins, every millisecond counts, because every second that you're computing is seconds you're not moving. And everybody, this is the big issue. It's all about picks per second, successful picks per second, per hour, I'm sorry, picks per hour. So everybody cares about that, and humans are like 300, and if you're slower than that, won't even talk to you. So you have to be faster. So spend a lot of time basically getting that resulting network to run really fast. That network can can check a particular grasp and give us an estimate of the probability in a few microseconds. It's very, very fast. Yeah, and why? Because we're using GPUs. So GPUs let us do that forward computation very quickly, and then we can run that for a cycle for a few hundred different grasps, and we can find that optimal grasp in the order of 20 milliseconds. It's amazingly fast. Yeah. Then we actually have the biggest thing that takes us right now is we have to compute the motion of the arm to get to that grasp, which is tricky because there's other objects in the bin. So it's not as hard, it's not much of a problem when you're dealing with an open bin, but when you're reaching down into a bin, especially once it's sort of in the bottom, then the motion planning problem starts dominating. So that's a problem. And then you want a fast motion that's not going to be too fast so that the object flies out of the section cup. So that was a paper actually we just presented 2 weeks ago at Wafer, which is we now are able to, we have an approach to optimizing the transport with suction. So we model the suction, and now we do this optimization to minimize the, ensure that the suction constraints are met as we do the motion. So it's, again, it's, these are great questions, and that's exactly what that we're pushing against, is how to get that faster and in production, because there's, it's very interesting to me that we get these things to work in a lab setting, and we're very, proud of this. But then you go into industry, they don't care, by the way, if you use any kind of fancy, numerical integration breakthrough or anything like that. They just want to know, is it going to work? Is it going to save them money? And so it has to be reliable. It has to be fast. So that's really the battle right now, and this is really just pushing down the speeds. And that's really where it's exciting. It's like a space race. There's a few competitors out there really trying to push that envelope. Good. Okay.
And do you use force feedback to grasp?
No, interesting. Okay, yeah, so that's great. We don't use any force feedback. We don't use any force feedback or any tactile sensing on the grippers. And here's my argument there. I would say that, one thing I've learned is that you can always add more sensors. The challenge is that every time you add a sensor, you also add a source of noise and potential failure. So we did some experiments with those. The current sensors that are out there, and there's gel sight, there's actually some really nice tactile sensors. Of course, force sensors are also fairly reliable technology, but they will often give you false readings. Okay. So force is tricky because you're holding something and then sometimes it's moving, right? And that taking the moment to let it stabilize takes time. And in the force sensor, you often get these false positives or false negatives when it will tell you the grasp has failed when it didn't. Okay. Right? So vision is what we use for the most part. And but we are experimenting. So these new sensors, gel sight sensors, are very popular at the ACRA conference. A lot of people are looking at them now. Facebook has a new version that's very low cost. So I'm not opposed. I actually started working on tactile sensing as an undergrad. That was my senior thesis. So I still think it's interesting, but it's but in industry, I can say it's probably it's not practical yet. Yeah. Yes.
So where you show the robots doing the reinforcement learning, you are just use vision. Yeah, in the beginning, when you show a lot of robots learning how to grasp, you are just using vision.
Oh, good question. No, that wasn't me. That was you mean the Google project. When they did the reinforcement learning, what did they use? I think it was just vision. Yes. Oh yeah. So they are very big believers that they're trying to do this. They're really arguing they want to learn how to do this as humans do it. So they don't want to use any kind of sensing. They don't use 3D cameras. So that's a good point. So let me stay on that for a second. There's some researchers in the field who want to really want to do things like humans do. So they don't want to use a 3D camera because they consider that cheating. So I respect that, but that's not. I'm trying to solve this problem. So I'm going to use every sensor. I'm going to use a sensor that I think is going to be helpful. Not every sensor, right? Because I could throw more sensors at it, but I think that could be detrimental. But the depth sensor, I do believe, is a big advantage, because that's what you care about is the is the three-dimensional geometry. And in fact, RGB cameras can be problematic because if you use that, then you're getting distracted by all the surface coloring and, coloring and texture. So you almost want to throw that out and just use the 3D images. And so that's what we do. That's a big difference between us and the Google. Thank you for pointing that out. Good. All right. Thank you guys for your patience for being here today.
One more?
One more question? Okay, but I'll also stick around if you want to ask me after.
He was preparing these questions since this morning in class.
All right. Oh my God. Now I'm in trouble. You're gonna crush me on this question. Okay, go ahead.
Oh, well, I'm going to take off my mask so I can be clearer. Right. So, how far do you believe we are from commercially viable graspers, since you mentioned that there are like many sensors involved and it's like hugely expensive in in computing terms. So, when do you think like, not enormous companies could use this kind of technology?
Great question. So is this going to be commercially practical, right? So I would say that's actually that's the question that Ambi is looking at, right? And first of all, we're not there for home robots yet. Although we were talking about this morning, I hope to have one by the time I need one, which will be a couple years. But I would love to have a robot at home rather than a human caretaker, frankly. So I'd like a robot that I some way I would feel like I would trust a robot more around my house than some stranger, that I don't know. But that's going to take some time. It is being worked on, and Toyota, for example, is one company that's actually making a major effort into commercializing home robots because of the huge problem in Japan with seniors and the changing demographics. And I think that's probably happening in Brazil too, right? It's all around the world. And by the way, that's not like some prediction, we're not sure it's going to happen. We know, by the birth rate, we know that we are changing the demographics and we're going to have a lot of older people to take care of very soon. So that's a big problem. But I think that we'll have progress and something that will work, not do everything, but do certain things around the house in the next decade. But where I do think it's practical right now is in these problems in logistics and sorting objects. And that, is really, we couldn't have done this 10 years ago because the technology wasn't there. But now it's here and the demand for logistics has gone up because of COVID, which we didn't predict. And so all those things have come together so that there's real economics that make it make sense. So I'm seeing this because I'm sitting in on these meetings every week, and we're still trying to convince certain of the customers, but a number of them are starting to see it actually practical. So I think there's real hope. I mean, that's an area, I'm not saying we're going to necessarily succeed. It's very competitive and a lot of things can go wrong, but I think someone is going to succeed and we're going to start seeing a lot of good automation in those settings. I do not think that it's going to mean that people are going to be unemployed, because I think what it's going to mean is that these are jobs nobody wants to do. There's a lot of jobs that we really do need people to do. So don't worry, by the way, and reassure your friends. Robots are not going to take over, but they're going to start doing things and make our lives better. I do believe that.
Can I have another question? Sure. It seemed that the Dexnet 4.0 had a preference for the suction cup. Do you have any explanation for it? The Dexnet 4.0 had a preference for the suction cup. Well, or at least it seemed to have.
Yeah, you knew that. Okay, very good. You read that paper, good. So Dexnet 4.0 had a preference for the suction cup, and that is something we don't quite understand why, but just with the mix of objects, the suction cup in that computation often won, and it wanted to use the suction cup more than the gripper. That is also, industry has told us that as well. They have actually said, we don't even want the gripper, because we can do everything with the suction cup. So, I don't know, it's kind of empirical, but I think it depends on your objects. So obviously, if you have a bunch of porous objects, suction cup's not going to work for you, right? So you're going to need them. But in practice, a lot of the objects that we encountered were amenable to suction. So that was just an observation that, again, somewhat, we live in an empirical science, right? We try to try things out. We try them in real robots and see how they work, but it's still fairly unpredictable.
Thank you.
That's a very good point. Very good point. So can we make packaging that makes this whole job easier? And I think that's a great point. And in fact, you see that in Amazon, right? They started streamlining their packaging to be more eco-friendly and more consistent. And so, yes, and that is possible. In general, it's very hard because in postal systems, people can still drop anything into a post office. And so companies are unreluctant to do that because they don't see any real incentive. But big companies like Amazon and Walmart and others, they are starting to move to making their objects, putting barcodes like all over, not just in one spot, is a similar step, but making the packages more amenable to grasping is very interesting. And I think that actually was relevant, and maybe that's a good point to close on, which is the design for robotics is really interesting. So imagine that in the future home, we've actually designed the objects like our plates and our silverware and everything else to be pick-upable, graspable by our robot, right? That's maybe the way we go in the future.
If you can't solve the problem, redefine it.
Redefine it, exactly. All right, great point to end on. All right, thank you guys, I really appreciate it. Thank you for coming.
Okay, thank you very much for this wonderful talk, and thank you for reserving your time in Rio to lecture us in grasping, robotic grasping. Thank you very much. We appreciate a lot. Okay, I think that we can close the transmission, and thank you very much. Bom, muito obrigado a vocês, e gostei de ver o pessoal da graduação aqui, aproveitando essa oportunidade que não todo mundo tem no Brasil, né? Qualquer pessoa que vem aqui no Brasil, estrangeiro, vai passar pelo Rio. E vai passar aqui pela COP, UFRJ, né? Então a gente tem que aproveitar essas oportunidades. Beleza? Muito obrigado.